So I'm going to highlight work that's been done. So at the Hopkins lab, which I co-directed with Ben Passy, and we've moved ship to University of Michigan, but this is our students and postdocs, and not everybody, but a lot of them. A lot of the collaborators in the work that I'll sort of mention, I won't maybe get to all of it, but some of it you'll sort of recognize some. You'll recognize the SIRFER and the IsoCamp influence strongly. So the force runs deep in these studies. So Leslie Chesson's been involved. We did a tap water study, which so the apple doesn't fall far from the tree. We've been involved with Renee Brooks doing some work in terms of precipitation and rivers. And so we've looked at plant waters. I've applied this to a lake record, which I'm not going to have time to talk about. But if you guys are interested in seeing how this is applied to lake carbonates, if I can have time, I'll talk about an application and how we're translating this to teeth. Ben Passy and his student Huanting Hu have been working on this, and on the PCO2 proxy. Huanting just submitted a paper on looking at a body water model of 17O. For how 17O works. I know I said, oh wait, I should be recording that anomaly right in my bones. Well, Huanting's like, okay, well let's develop a model to really understand how it should work. So then what we should expect when we actually measure it in the dinosaurs to get PCO2. So her first paper is a modeling paper with eggshell. We went all over the place collecting duck and chicken eggs and everything to try to understand how does this work in eggshells today, right? Our goal is PCO2, right? But like we really need to understand the systematics and what levers really matter, right? And this question and what they're really, and so that's step one. And the next step for that dinosaur eggshell study is actually then another model looking at GPP and how much these stratospheric influence, so really understanding the limitations of it and then applying it. So it's slow, steady work, but the yields, I think, are going to be high. So Xuning Li is somebody who I'll focus on her work a lot. She came to my lab before we could even measure 17O in waters, and so she did a lot of the groundbreaking work with the idea to looking at lakes and carbonates in the geologic record, but we needed to do this basic stuff first. So Hao Yuan has worked on lakes, Nikki's worked on lakes too, Sophie's worked on 17O of tooth enamel and the modern study that maybe I'll get to, and Jessica Mormon's a postdoc who's still working with me and applying this to southern Kenya as well, to some lake cores. So it's a whole team that we're working on, and we're continuing this work at University of Michigan. Okay, so I wanted to talk to you about, in the time that I have, to talk about the basics of triple oxygen isotope fractionation in water. And then we'll talk about highlighting new work that gives some examples of 17O data from continental waters in the US. And then if we have time, to talk about the tooth enamel story. Okay, so I'm going to be now focusing within this ellipse. So all of the variation we're talking about, and this is why we're going to move from that per mil scale to this per mig. So that stratospheric CO2, those rocket samples, those had per mil deviations from an expected line. I'm now going to be looking at per meg deviations from an expected line, and this is why we had to kind of overcome those hurdles. So why did I do this? Because when we use delta 18O based records, there's so many different things that can influence delta 18O, and so if we had some sort of extra lever, if we can reduce the degrees of freedom in our system just a little bit, then we would be able to make progress. So we need additional ways to constrain kinetic fractionation in hydrologic and ecological systems. So that's a lot of evaporation, but diffusion. Kinetic fractionation, and if you want to get evaporation, you can do this. DXS, that's great if you have modern samples. It's very hard to actually get deuterium and oxygen preserved in the same material in the geologic record. You can do it, you can do different materials, so you have lithoaxes record deuterium isotopes, and carbonates or silicates might record oxygen isotopes, but in the same material, it's really hard to get. And so this might give us a chance to do that. So now we're at the point where we can make high precision measurements of this CAP72 in water, which means that we can work within that gray ellipse. So small variations in triple oxygen isotope distributions of waters can be measured, and we can now start to document the kind of variation we see. And once we understand it in the hydrosphere, then we can then extend to the geologic record. So slow and steady. I'm a pretty patient person. Okay, so this basic terminology again. So we have this delta 18O value. And the 17O value, and equilibrium processes will define this slope of this process as a lambda value. And you can say, okay, I'm going to define my lambda, my reference of my slope as the equilibrium line, or maybe the equilibrium line slightly less than that. And then there's a slope, these kinetic processes, and this is one big take-home message that you can take home from this whole thing, is that kinetic processes usually in these triple isotope systems have a lower slope. Okay? Is that how DXS works? This is evaporation, right? Yeah. It works, it's the same way. So just like when you're sort of confused and lost, just replace 17O with delta D. And then like, okay, I get it. It works the same. And I'll show you experimental data where we can actually see it in the same way. And when kinetic processes are driving both d-excess and 17O-excess or cap 17O, they correlate beautifully. Okay. So there's another thing. So these deviations are so small that this cartoon can't be drawn on scale, because basically the differences in the slope between kinetic and equilibrium fractionation, I'll just put it up here just so you have a reference, the migrating chalk. But just so you have a reference, so instead of 0.5, so this slope, instead of being 0.5 for equilibrium processes, it's thought of, for water, it's actually thought of being 0.529. This is equilibrium. And for a pure evaporation, it would, for kinetic, for water, it would be 0.518. So it's seeing the differences in a slope of 0.529 and 0.518. All right? You can't see that. And so I'm actually not going to plot a lot of things in little delta space, because the plots visually don't do anything for you. Okay? So I'm looking at the deviations in a slope of 0.528 and 0.518. Right? That's something that, this is why we have these per meg differences. Okay. We use, there's another sort of trick that we use, and I'm going to show you everything in these delta prime notations. And so and the reason why is this relationship is actually, the relationship between delta 18O and delta 17O is actually not linear. And you know what? It's not linear for delta 18O and delta D either. I hate to admit it to you, but this is the relationship. So these delta values, you can basically translate them into alpha values, right? And they relate to each other, and this applies to everything that this 17O of alpha relates to 18O of alpha. It's a power law relationship, okay? So there's no way that these deltas actually should relate to each other in a linear way, okay? And I'll convince you to you for deuterium as well. We have to in order to actually put these into a linear relationship, we actually have to transform them using this delta prime notation, which is just, it's a log transformation of it, basically, so that we can see these two different things in a linear space. And I'll get to that in a moment to explain it. Okay, and so this is these official definitions of this cap 17O, this deviation from an expected is your measured little delta 17O minus whatever you decide your reference lambda is, your reference slope is, this reference relationship is times your delta 18O. Okay, so it's a similar thing as your dxs. And I'll refer to cap 17O and 17O excess interchangeably, and 1 per meg equals 0.001 per mil. So what's up with this delta prime notation? Has anyone seen that before? It makes everything messier, but we realize that. So this is from this ILO review paper, and I just want to include it so that if you look at the paper, you have this reference in. But these R values are ratio values for so this would be R18 versus R17, or, you can think of it as in there's a 34S or 33S. You can also sort of think about this in 18O and deuterium, that the relationships between them is actually curved, because it's because these alphas are related in terms of a power law. So it's actually a curved relationship. So we need to do some sort of law. If we're actually going to look at the deviation from this relationship, we want it. It's going to be a lot simpler if that relationship is straight and it's not curved. Okay. So we do that by actually plotting them in some sort of log transform. So you can either transform the ratios or transform the delta values. I'm going to present things in delta values, but if you ever do any modeling of this stuff, or you're modeling anything, always work in ratios. I don't know like who the cruel person was who basically decided delta values. I mean, ratios are just, delta values are useful to handle with, but when you're actually trying to, if you're having trouble modeling something and things are getting really confusing in delta values, just convert everything to ratios and your life will get a lot simpler. It's the same thing with modeling this. Okay. Oh, right, and this slide's not included either. Okay, so why do we use this delta notation? I just want to walk you through this little example because to me it's really useful to see. So this is we have some sort of slope, which is some sort of relationship between these delta values. And it's this power law. You can define it. It's a theoretical. It's been defined theoretically for different materials. You can look up these theoretical equilibrium relationships between these different materials. Okay, so you'll see theta or you'll see lambda as this slope here. So I want to sort of show you how this works, and I want to show this to you with delta 18O and delta D, and something that sort of makes sense. So you guys can look at the relationship. So we all know that we have a relationship that we think about all the time, right? Do you know what drives the slope of 8 between delta 18O and delta D? Why is it a slope of 8? So it is really, it's an equilibrium fractionation that you could basically, it's sort of the, if you think about equilibrium, equilibrium fractionation for delta ATNO and delta D, the ratios for, it's the ratios of those different fractionation factors should be 8, okay? So you can come up with it just from equilibrium fractionation. So we can actually do this. So if you look at alpha liquid to vapor and just a Rayleigh distillation model, let's say you can look this up, 0.01098 at 20 degrees C. You can make this as I purposely just copied this out of Excel so that it would seem accessible, that you can just sort of do these calculations. You can look at these different, you can take these two different fractionation factors and the power law of them, you can basically calculate a theta for them, which is basically 8.4, okay? So you can take all these different points for just a Rayleigh distillation, and you can plot all of those different points for every liquid point, for every delta ATNO point, there's a delta D point, and you can plot delta ATNO of liquid versus delta D of liquid, and you can have some sort of relationship. Is this a straight line? It's not a straight line. And it makes sense because it actually shouldn't be a straight line because those alphas relate to each other as a function of, they shouldn't necessarily relate to each other. You can convert them. You can basically make the delta prime notation. And when you make these deltas values into delta prime, this becomes a straight line. Okay? So you can sort of work this through. But you can, the reason why this matters is this curvature actually, we don't bother with delta prime notation in this space because it doesn't matter in terms of the deviation and the scales at which we're working. But it actually does really end up mattering the scales at which we work with delta 17O, okay? So this is a good thing of you don't go to the trouble of it if it's not worth it, right? So there's a lot of approximations that we just sort of assume. Let's see. Okay, so that same thing works in delta 18O and 17O space. Okay, so we've basically sort of getting back to this slide that I had earlier that wasn't in the talk, your notes. But it's this improved analytical methods and standardization approaches that have enabled us to sort of move within that gray ellipse of the hydrosphere. And so in 17O space. And I'm just going to present this. If anyone's interested in the methods or the techniques, I'm happy to talk to you about it. But I'm going to just mention them. But what we do is we don't need very much water. We inject 3 microliters of water. And we fluorinate the water. So we can't, here's the rub. I used to always work with CO2. CO2 is such a great gas to handle and work with, but I can't work with CO2 if I'm going to measure 17O, right? It's the same reason why you don't like 17O is that I can't separate out, there's way more of that 13C in there, so I can't separate it out. So I can't use CO2 as my analyte, which is frustrating. I need to use O2. That is really frustrating because guess what? O2 does not freeze at liquid nitrogen temperatures. That is a major bummer. It does freeze at liquid nitrogen in a molecular sieve, okay? So we can freeze it. But basically, we have this reaction where we inject water onto hot cobalt trifluoride, we produce O2 cobalt difluoride, which is this pink crummy stuff, and HF, but we're not actually generating that much HF because we're not actually putting in that much water, okay? And then we take that O2, we clean it up, and then we put it into a dual inlet mass spec, MAT 253. People have done these on deltas as well. We sit on it and we analyze it a long time. We probably analyze it more than we need to. At Michigan, we're trying to speed up the process. But part of the reason why you need to analyze this a lot is because there's not a lot of it in there in your sample, right? So you just need to make sure you use your advantage of counting statistics, right? To say, I'm just going to keep measuring it. And if I measure it enough times, I'll get the right answer, okay? And it's it's a statistical approach. Just keep doing it. So we calibrate it to SMO and SLAP. There's a whole nerdy discussion in terms of how do you calibrate this, but there's enough labs that are doing this. So the labs, there's several labs now that are running this in terms of the fluorination approach and using IRMS. There are other labs also that the Picara has an instrument, LGR has instruments. Those instruments are coming up, but this is from a calibration study that we did with the LGR instrument with different measurements, and this is in 17O excess versus cap 17O and per meg. And these are, this is 0.1 per mil, 0.2 per mil, 0.3 per mil, and we're getting pretty good agreement between different standards. If you guys are wondering why we get better, this is not the method that you want to use to measure delta 18O of water precisely, but we get really good precision. We can probably anywhere from 5 to 8 per meg in 17O, and the reason why our precision of cap 17O is better than our precision of the little delta values. Reviewers don't like this if you haven't thought about this but if I'm measuring delta 18O, delta 17O, and all of my measurements are happening, and all of my error is mass dependent, right? So all of my error is happening along here, right? So I might not be able to constrain this very well. So I might have a lot of error in here, but this error can be very small, right? That sort of makes sense. So my errors are correlated. So because my errors are correlated, the deviation, which is what I'm looking at, is actually smaller. So it's, here again, I can go into that in more detail, but we can sort of take advantage of the fact that our errors are correlated to actually make sure that we have small precision on this.